Welcome everyone in Mechanical Unit Operation course discussion. Good evening and happy Teachers Day to all. Now, since last couple of the weeks, we discuss about the solid interaction, solid size reduction, solid particle separation, and other than that, solid agglomeration also. Now, today we start the discussion on the fluid and solid particle interactions and various correlations and various phenomena around it. Okay, so I am sharing my screen now. Hope so everyone can able to see my screen. And here we start today's discussion. So as always, I started to discussing the major points which are there in the subjects, some theoretical backgrounds of the subject and sub of the chapter, and at the same time I touch all the conceptual learning on the basis assignment questions are there. Okay, so the week 6 discussion is flow path beloved bodies. So there are mainly 4 lectures. First is what is actually flow path immersed solid objects are there, and then a couple of lectures discussing about the motion of particle through fluids. Okay, so at this moment I also want to thank and wish happy Teachers Day to our Professor Mendaki sir also. Okay, so this is the outline of the today's discussion. We start with what is the importance of solid liquid systems. I again touch the theoretical parts which is there from the textbooks, and it is important because many of your assignment questions are directly based on the theoretical sections. Then we discuss about the wall of immersed object making an angle with the direction flow. That means immersed object force calculation will be there. Then we discuss about the drag coefficient. Most of the things you already discussed in the briefly in your physics or maybe in the fluid mechanics subject. But here we will go through the more detail about according to our requirements. Then we start we discuss about the one-dimensional motion of particle through fluid. Then what are the criteria for settling regime? And couple of the examples, and one important topic I also want to touch, that is a hindered settling. Okay, so first is okay, just don't consider the number of the lecture, it's a 17 only. Flow path immersed solid objects. So first we start with what is the importance of solid liquid system. Till now we discuss about the solid particle separation, size reduction as well as agglomeration, but most of the time we encounter with the solid liquid reactions and solid liquid interactions in the industry. So first is why it is important. So relative flow between solid and fluid, or both solid and fluid moving, is very common, as it is much more common than the solid availability in the industry. So mainly that's why such a solid flow system, there are many components are important, but we need to discuss about the drag. So whenever our solid particle is taking interact with liquid, then what is the drag force it is facing, or what is the final magnitude of the drag force, what is actual drag force, what are these components. There is one buoyancy force is there, and gravitational force are there. All three forces are much more important to go for the calculation for this solid liquid system. Then there is by Newton's third law we can say that an equal and opposite net force is exerted by the object on the fluid. Obviously, as we currently discuss, at the end if we follow the Newton's third law, then all the forces are equate with each other, and at the end opposite net force is also provided. So firstly, if we talk about the drag, because drag is important in the solid liquid system, I didn't cover everything in this presentation. All the main point I covered, and there may be sufficient information is there for you to solve your examples problem as well as your theoretical assignment problem. So drag has two components, okay, form drag or pressure drag. This all maybe we already know. So obviously when drag force is acting on the surface, then maybe you can consider the pressure which is acting on it, and at the same time if it is acting on any solid particle surface, then there may be chances of wall drag or some friction is here, so that is also responsible for the drag to occur. So that's why form drag or post pressure drag, as well as the another component is the wall drag, friction drag or shear drag. We have many name of the other component according to the acting of force. You can consider any of it. So now we have to understand what are the components of these drag forces and how they actually give you the resultant value for their interactions, as well as the according to their angles which is formed when drag force was interacted with the solid surface. So this is the very common figure. We always maybe encounter this kind of figure in past also, that this is the force, as you can see here, and here force from the pressure is also applied from here, and there is a wall drag is there. This is a solid surface, so flow direction is in this direction. So basically you can see that pressure is P, but pressure is equal to force upon area. So pressure force is equal to P into A. Here we consider the small particle on this surface, which is, and denote the area of the particle as dA. Then we can say that force P is equal to pressure force is equal to PdA. And if here the angle which is making by that force is known as alpha. So here this angle is 90 minus alpha. His angle is also 90 minus alpha. Here, because of this is also alpha. This is 90 minus alpha. So like this you can consider, and this is a wall drag. For wall drag, tau W sin alpha dA. How it came? So first of all, we select the area of dA. Then angle of inclination to the direction of flow is 90 minus alpha. As you can consider, this angle of action is 90 minus alpha. Component of the wall shear in the direction of the flow contributes to the drag. Obviously that is one part of drag, one component of drag. Another contribute causes the fluid pressure which acts in the direction normal to the wall. Now drag comes from the pressure component in the direction of the flow, and the total drag on the element area is the sum of the two components. So obviously one is this component, another is this component. The total area is the sum of the two components. So I am not going into the much detail, as professor rightly in-depth understanding was provided by him, and rightly give you explanation of this all kind of interaction. And at the end you will get one wall drag component, which is a tau W sin alpha dA. Another is a P cos alpha dA, which is a form drag component, which acts as a resultant, which acts as a summation. If we take both the component, then we can get the resultant drag force. Okay, so here, as we mentioned, that wall drag is tau W sin alpha dA. You can remember this component, and we can easily derive from the figure also. Form drag is equal to P cos alpha dA. Now total drag and element of area dA is equal to sum of the integral of these two quantities. So obviously for the total drag, if you want to calculate, then we need to take the sum of both these quantity. Then you can say that total drag for entire object surface is equal to So this is if you want to get if you only consider the area dA, then total drag is the summation. But if you want to consider the total drag on the object, the surface of the object, then you have to take the integral of total drag which you got on its element dA. If you take the integration of the total drag at dA, and then you will get the total drag for the entire object surface. Okay, it's very easy. You don't need to perform any calculation though. Now, so this is the important phenomena when any flow is flowing in particular direction or in a streamlined manner or any other manner, but mostly we are focusing on the streamlined manner. And if we put any very thin plate in the same direction of the flow, then there may be the different interaction between the flow as well as the this plate, and because of that there will be change in the flow direction, or there will be change in the pressure and velocity component of the flow. But at the same time, if we put this thin plate as like vertically, then there will be very much important effect you can observe. So this all thing we can discuss in a little brief. So if we talk about the very thin plate flow parallel with the plate, so flow is parallel with the plate, so only drag force is wall shear tau w per unit project area of the thin plate. Drag force is only the unit projected area of this plate. And you can see that direction of the flow, if you consider, is like this, and this is the plate, this is uniform velocity. You can see that the velocity component is different, the value of velocity is different in this section as well as this section. This velocity varies from this uniform velocity. Here you can see all the velocity component is different, that's why it is varying. So if we put the very thin plate in between the flow, then you can consider this kind of effect may be there. And another phenomena, as you consider, if we can put the thin plate and the vertical condition, so then we consider that when we go for the horizontal condition, only form or wall drag is there. When we consider the vertical direction, then the drag is due to the pressure component only. So as you can see here, we put the plate in the vertical condition, then because of plate, this streamline of motion of the flow it got disturbed, and here you can say low pressure zone and eddies was generated, or as it will be generated. So these are the low pressure zone, or that is also known as the wake formation. So whenever you are putting the plate in the vertical direction or the 90-degree or normal in the normal direction of the flow, then you can consider that there is a huge change in the flow, and that's why we can consider that the pressure component has many effects, more effects than the you can say than the shear component or form drag component, the pressure. And you can see there eddies are generated, but although there are uniformity in the eddies generation, if we go for more flows change and all, then there will be there is some constant speed of this flow, then there is some constant Reynolds value. If we increase the Reynolds value, then there you will see the different pattern of flow like this. If our Reynolds number is close to 0, then you can consider that the flow regime is the creeping flow, and there may be steady flow generation is there is no wake formation is there. So flow characterization of the flow is steady. But if we talk about, these are some arbitrary for the understanding, I am presenting some arbitrary concept. So you don't have to consider that which kind of Reynolds number is there, and according to the different kind of Reynolds number, this is for the you can say sphere, but according to the different shape and different flow profiles as well as different kind of your flow is taking place on the surface, taking place on the cylinder. Depending upon that, the value of the Reynolds number will be different. If we talk about the Reynolds number between 3 to 30 or 4 to 40, then vortex pairs index. You can see small vortex pair is generated. Although the flow characteristic is all still flow flow is still steady. Excuse me, just yeah. Here are some messages shown on another computer. So there we can see the symmetric or separation is still there. If we talk about the 30 to 80 or 40 to 90, then it is known as the onset of Kalman vortex state. So it is still laminar, but unstable wave formation will be started, and after that it is converted into the Kalman vortex state. So if we further increase the Reynolds number, then pure Kalman vortex state, you can consider that they are not symmetrical in nature, and due to that the whole streamline motion will be disturbed. And if you go for a much more higher Reynolds number, then there is a laminar flow still maintained with vortex state instabilities. And then after that, if you go for more high Reynolds number, more than 10 to power 5 and to 10 to power 6, some value of 10 to power 6, then it is known as a critical region. And then in the critical region, turbulence of flow is started, then laminar separation is started, then turbulent wake, turbulent reattachment will be there. And more than this 3.5 to 10 to power 6, you go into the supercritical regime. And as you can see, whole flow is in the zone of turbulent separation. So these are the kind of Reynolds number regime you can consider, and depending on your what is the impact and characteristic of flow will be encountered after you going for this different Reynolds number series. Okay, then we discuss about the drag coefficient. As we till now we discuss a lot about drag and how it is affected. We understand the physical significance of the drag, but what is the equation and how can we get the value of the drag? So for that, this discussion is required. So for flow through pipes and channels, friction factor, we all know that maybe you may be aware about it, that in fluid mechanics we consider the friction factor. And friction factor has the definition of wall shear stress divided by the ratio of the wall shear stress or velocity head, and the product of velocity head and density. So we are not going into much detail, but yeah, it's tau w by rho v square, density into velocity head is v square by 2. So v square by 2 is the velocity head. In Bernoulli equation also we know. So that is that friction factor is a value of wall shear stress divided by velocity head into density. That is tau w by rho v square by 2. So this the same analogy for immersed solid object. We consider for the friction factor for the pipes and channels, his flow is there and friction is generated. The same, if we consider the same kind of analogy for solid particles are there and they are flowing and there is some friction is generated, then the drag coefficient defined as the total drag force per unit area divided by velocity head into density. So the bottom product is the same only. And here we discuss about the shear stress. This is nothing but the force, shear force by area. Same here, the drag force by unit area, which is FD by AP. So here this is the definition of the CD, which is nothing but the drag coefficient. D is denoted by the drag and C is the coefficient. CD is the drag coefficient, and the value is FD by A upon rho v square by 2. So this is how we can calculate the drag coefficient, and this is important when you are discussing about the various examples and various different kind of phenomena, where you at the end you will require the drag coefficient to be known. If you want to calculate the terminal velocity, if you want to calculate the Reynolds number, sometimes that all this require this drag coefficient. Now in this equation there are nomenclature is denoted that Fd is the total drag force. We already have seen that Fd is the total drag force, Ap is the projected area, density of the particle, velocity. So Fd by the density of the fluid, not particle, sorry. Rho p is density of the particle, and V is the uniform velocity of the fluid or approaching velocity of the fluid, and Fd by Ap is the average drag per unit area, and Ap is the projected area of the solid. So as anyone can understand, it's not that much complex. And in exam or in assignment, if you haven't find any problem in which they ask for to calculate the drag coefficient, then you should have known about what are the different nomenclatures are there, what are the different details are given, data is there, how can you calculate the things like Fd by P upon rho square by 2. If you have all the values, you can just substitute the value into the equation, and if you don't have any, then you need to find the one, and then at the end you will get the drag force. Now projected area of the solid, so better I just okay, so I have pointer now. So what is a projected area? This is the definition of the projected area of the solid object. So basically area obtained by projecting the object on a plane perpendicular to the direction of the flow. So as you can consider here, this is the direction of the flow, and here I have one cylinder, and if we can put the cylinder like this is the perpendicular to the flow, and you can see this circle is the, as you can consider that the first sphere, the circle is the object or shape which is there in this area is there, the surface area of the circle you need to consider whenever you use this kind of cylindrical pipe or some sphere or something, where if you same the same sphere you will get the same circle. If you are discussing about cube, then you will get the projected surface is square. So like this you need to consider according to your geometry and what you have put the geometry of the object which you put in the flow. So according to that, area obtained by projecting the object on a plane perpendicular to the direction of the flow, that area is known as a projected area, and it also refers as the area of particle that is seen by the fluid. Okay, so fluid can only see this circle, fluid can only see this square, so that's why fluid just interacting with this kind of geometries only. So we need to consider the area of that geometry. If we talk about like sphere, the projected area is that of the circle, so we need to find the circle area of the circle, which is nothing but the pi r square. Or if you don't have the value of the radius, then you can consider the diameter of circle, which is nothing but pi dp square by 4, where dp is the diameter of the sphere. And if we talk about the projected area of a cylinder with its axis perpendicular to the flow direction, okay, so here I consider the axis is in the flow direction. If we have the cylinder with axis perpendicular to the flow direction, then you can consider it as okay. Here I need to consider the rectangle is the projected area of cylinder. So that's why A is equal to L into dp, where L is the length and dp is the diameter of the cylinder. So diameter is considered as the dp and A, and you can consider A equal to L dp. Now projected area of cylinder with its axial parallel to the flow direction. Okay, we consider the axial is the parallel to the flow direction, then it's not perpendicular, then you can consider it's a circle, and then the area of circle is pi r square. For a cubes of equal size, as we consider cube, then the area is the square area of the square geometry. Then square geometry is the symbol L into L or S square. So this is how you can consider the projected area in your calculation. Now for the calculation we consider some of the parameters. Parameters are the dp, particle diameter, rho, density of the fluid, v, velocity of the fluid, mu, viscosity of the fluid, cd is the drag coefficient. Now from dimensional analysis we can consider that drag coefficients is a function of the Reynolds number of the particle. So where REP is the Reynolds number for particle in a fluid, where our particle is in the fluid, and then we find out the Reynolds number for this, then it is known as the Reynolds number for particle in a fluid. And we know that the definition of Reynolds number is density, velocity as well as particle diameter divided by the viscosity of the fluid, rho v dB by mu. If all dimensions of the object are not equal, as in the case of sphere, then drag coefficient may depend on the shape factor and orientation of the object. So this is generally Reynolds number is a dimensionless number. Sometimes if our dimensions are not equal, or sometimes if we consider the sphere, then mainly our dimensions are not equal. Then we need to consider what is the shape factor of the particular object and what is the orientation of the object. But the consideration of all these parameters, we can at the end we can find the Reynolds number of the particle in a fluid. Now different coefficient, drag coefficient and Reynolds number in the particle in fluid relation exists for each shape and orientation. Yeah, definitely according to the shape and orientation there is a different relations are exist. Okay, so this is only the discussion about as you all know, maybe you all remember all the formulas or terminal velocity, but for this all we just consider the terminal velocity derivation for sphere. You can find some problem in your assignment on the basis of the same final equation. So for understanding that, we just go through the spherical particles calculation of drag forces, drag coefficient and terminal velocity. So for spherical particles settling in a Newtonian fluid at REP less than 0.1, so we need to consider that if we just consider the Reynolds number less than 0.1, then there is Stokes law region is there. So we have to follow the Stokes law region. In the Stokes law region, this is the Stokes law that drag force is given by 3 pi mu v dp. This is the Stokes law. So the value of CD is equal to FD by AP upon 0.5 rho v square or rho v square by 2. So here if we have to substitute the Stokes law instead of FD, and if we substitute the Stokes law 3 pi mu v dp and 0.5 rho v square, and instead of projected area for spherical particle is there, that's why we have to consider the area of the circle, which is the pi dp square by 4. And if you just clarified all the thing and solve it out, and at the end you will get that for the REP less than 0.1, then your drag coefficient value is given by 24 divided by the Reynolds number of particle in the fluid. And in such low Reynolds number of particle in the fluid, then terminal velocity of the sphere is given by velocity v is equal to g dp square delta rho divided by 18 mu. This is a very well-known equation, and if we just consider the Stokes law regime, then our terminal velocity is directly proportional to the square of our particle diameter. You have to remember all these things, because in sometimes GATE examination and other examination directly ask the question for using this kind of concept, that in the Stokes law regime your terminal velocity is directly proportional to the square of the particle diameter. Okay, so here some important facts like the FD or CD is varied only when Reynolds number of the particle is less than 1. This type of flow is called a creeping flow. Then further wall shear is the result of the viscous force only. Okay, so we have to consider, well, here only viscous force is prominent, that's why it is coming as the creeping flow, and at the end you will get the value of Reynolds number less than 0.1. That is, inertial force is negligible. So Reynolds number has the definition is inertial force, okay, divided by viscous force. So here as a value of Reynolds number is lower and viscous force is higher, the inertial force is also lower. So you can consider that the initial forces are very much negligible in here. And this law is valid for circulating the resistance of small particles such that dust or fogs moving through gases or such low viscosity fluids. So these are some of examples when this kind of law is pertinent. This kind of law is pertaining. The vortices in the recirculating wake dissipate considerable mechanical energy and cause the pressure to be much less than the upstream pressure. Okay, so if some vortice is generated, then it dissipates the mechanical energy and cause the pressure to be much less than the upstream pressure. So here we consider that it is a low pressure zone, a wake formation will be generated. This makes the form drag quite large relative to the drag caused by the wall shear. So that's why form drag has a value more than the wall shear drag. So if we consider the Reynolds number of particle in fluid more than 10 to power 3 to 10 to power 5 range, then CD is or drag coefficient is nearly constant at 0.4 or 0.45. So generally 0.44 or 0.45. Generally in most of the example or most of the place we consider the 0.44 is the coefficient. When we consider the Reynolds number value is much higher. When changing very slightly as the point of boundary layer separation slowly shifts towards the nose of the sphere. This law is known as the Newton's law. So the first law is when Reynolds number is low, then it is a Stokes law. When Reynolds number is low, when Reynolds number is much higher, then you can consider is a Newton's law pertaining in that particular area. And the value of this coefficient is constant, and you can consider the 0.44. And in the Stokes law, we proportional to dp square. In the Newton's law, we proportional to d raised to 0.5. That is the most important thing, that your particle diameter value is drastically reduced. This law applies only for fairly large particles falling in gases or low viscosity fluid, and terminal velocity is proportional to d raised to 0.5 or 1 upon d square. So one-dimensional motion of a particle through fluid. Generally, the equation, this equation is much important in order to get the final equation in terms of force balance. And here you can consider there is a two type of phenomena you can consider in the flow through the pipes in a horizontal direction or flow through the pipe in a vertical direction. If you consider the horizontal direction, then this is a flow direction, and this is the buoyancy force as well as the drag force, which is opposite direction. And at the same time, here is the gravitational force, acceleration force, and buoyancy force and drag force is the opposite direction. Projected area is AP. So external force, any external force you can consider. This is in terms of vertical, it's gravitational force. So consider a particle of mass m moving through a fluid under the action of the external force Fe. Let the velocity of particle relative to fluid du. These are some assumptions or consideration for the equation. Derivation of the equation: buoyant force is on the particle is Fb, considered as Fb. Drag force is considered as Fd, and acceleration of the particle is du by dt. So if you want to find the final equation of the drag force as well or the terminal velocity, if you want to derive the equation of the terminal velocity, then you need to consider the force balance. So in here the net force is equal to F is equal to acceleration. F is equal to m into acceleration. So m d by dt mu. M is a constant value, so you can consider out m du by dt. F external is in the same direction of the flow. Then buoyancy force and drag force is the opposite direction. That's why Fe minus Fd minus Fd. External force is MAE. Consider drag force is CD u square rho EP by 2. It's the same equation of CD. So Fd by AP upon rho u squared by 2. If you just make the rearrangement, at the end you will get a drag force value like this. And the buoyancy force is equal to Fv is equal to mass of fluid displaced. So buoyancy force, as you know, here if our solid particle is sphere and it is flowing like that, if it come to here, then it is displaced the mass which is over here, and it has some acceleration from the external force. So that's why you can calculate. That's how you can consider the buoyancy force calculation. And by Archimedes' principle, buoyant force is the product of mass of the fluid displaced by the particle and the acceleration from the external force. This is given from the Archimedes' principle. And how can we consider the mass? We can consider volume of the particle is m by rho p. So volume of fluid is displaced by the particle, and mass is just m by rho p is the volume of the particle, and the total mass is multiplied by the total density m by rho p into rho, and it is also again product multiplied with acceleration from the external force. So our force, buoyancy force is F is equal to Om by rho p into AE. Now here the force balance was taken place, and we don't want to go to the much detail, and at the end you will get the value of velocity or maximum velocity when you attain. Then du by dt is equal to 0 if you put, then maximum velocity you can attain, and it is known as a free settling velocity. So like this, if you consider the infinite cylinder, then after some time the particle has no any considered in constant velocity effect. It is not considering any acceleration. It is known as a du by dt is equal to 0. That is known as its a free settling velocity, and the equation is u2 is equal to under root of 2g into delta rho, which is rho p minus rho into m divided by ep rho p cd into rho. Now motion of the spherical particles. Here if you consider the spherical particles, then we need to put the value of the spherical particle. Then the diameter of the particle is dp. Then the whole equation is converted into the ut is equal to under root 4j delta rho dp upon 3 cd into rho. Now, so here again we consider that for low Reynolds number and what high Reynolds number, what is the difference in the terminal velocity or settling velocity or terminal velocity, you can consider any. CD is equal to 25 by RE. So 25 RE you have to put rho UD by mu, and then this value you have to put substitute in the value of CD, and then you will get the value of terminal velocity ut is equal to g dp square delta rho by 18 mu. This is the equation which I have seen earlier, and this is how we consider how it is getting derived. Now if we consider the high Reynolds number, which is more than 10 to power 3 to up to 2 into 10 to power 5, then we consider the value CD value is constant 0.44. We have to substitute the value in the above equation, then at the end you will get the terminal velocity is equal to 1.75 under root of g dp delta rho by rho. Now criteria for the settling regime of spherical particles. So there may be two regimes. One is a Stokes law regime and another is a Newton's law regime. So what are the criteria are there? So for Stokes law, we just see Reynolds number is equal to rho ut dp by mu, and according to that dp square dp if you substitute the value of ut, then at the end you will get dp cube g rho delta rho by 18 mu square. So here we are not going into the much more detail that how it is coming, but if we consider for the spherical particles, for all regimes, terminal velocity equation is under root 4g rho p minus rho dp 3 cd rho, and the value of k criteria is given by dp gp rho delta rho by mu square 1 by 3. Same if we consider the Stokes flow regime, then ut is equal to g dp square delta rho by 18 mu, we just seen, and the value of k is less than 2.6 criteria. And for the Newton's flow regime, we take 1.7 under g dp rho p minus rho upon rho, and k value is 68.9 to 236. Lower limit is 68.9. There may be some question on the basis of this also. These are my highest value 2360. So you can get the many your assignment problem solution like this. So in between 2.6 to 68.9, it is in the transition region. Then you have to consider the different value, or that you can consider this. So here example is that a spherical particle which has diameter of 51 mm is settling in a Newtonian fluid with terminal velocity of 20 meter per second, Here we have density of the fluid is 1.115 kilogram per meter cube. Viscosity of the fluid is 1.63 into 10 to the power minus 5 pascal into second. Then what is the value of the drag coefficient? This is the question. Now we know that the first of all we need to consider that which this spherical particle flow is going on to the Stokes flow regime. It has Reynolds number, it's lower Reynolds number or it's higher Reynolds number. So it is 10 to the power 4. So we consider it, and if according to that we can go for the value of CD. Lower Reynolds number than 24 by Reynolds number, if higher Reynolds number than 0.44 constant value you need to consider. Then here Reynolds number is higher, then you need to consider the CD value is more than 10 to power 3, then Reynolds number value is more than 10 to power 3, then CD is 0.44 or 0.45 approximately. You can consider 0.44. I added one extra questions in that. It's the settling of neutron and fluid. Here our Reynolds number is already given 7.2 into 10 to power minus 2, like 0.072 is the Reynolds number. Then which kind of value of drag coefficient is there? So as the Reynolds number is lower, then we can go for 24 by Reynolds number, and if we substitute the Reynolds number value 7.2 10 to power minus 3 minus 2, then you will get the value of drag coefficient is 33.33. This is how you can consider. First you need to always understand which is the flow regime is there according to Reynolds number. So you need to find the Reynolds number value, and from that you can substitute the value in your equations for getting the coefficient of this drag coefficient or many other terminal velocity and everything. You need to require for understanding of the flow regime first. Now there is one another example in which spherical particles of the size 4.82 millimeter, this is the diameter, are falling in a column of a height 79 meter. There is one column which has a height of 79 meter, and here you can contain air, and the density of the air is 1.115 kilogram per meter cube. And what is the viscosity of fluid air is 2.183 into 10 to the power minus 5 kilogram per meter into second. Assume fluid settling condition and obtain settling velocity of the single spherical particle if its density is 1745 kilogram per meter cube. So here particle density is given, and always they ask us to consider the free settling and find the settling velocity. Then dp value is a 4.82 millimeter, then 0.0048 meter. The density is 1.15 kilogram per meter cube. Mu and rho p all are given. Now first thing we need to find the value of k. So k, for finding the value of k, this is the equation. K is equal to dp. We all know that this equation is there, and if you don't know, just again go through the theoretical parts, particle parts, and you can easily find this equation. And it is the same equation, dp g rho delta rho by v square and raised to 1 by 3. If you substitute the value of all the quantities in it, then you will get the value of k is 164.88, which is obviously more than 68.9, and which is between the 68.9 and 2360. And you can go for the Newton's law regime, and you can find the terminal settling velocity like that. It settles in the Newton's law regime that you need to understand first before going to the further calculation, and that's why it has terminal velocity equation which we follow for the Newton's law regime. Ut is equal to 1.75 under root gdp rho p minus rho divided by rho. Now if you put the value in substitute the value in this equation, and then you will get the value of ut's terminal settling velocity is 8.6 meter per second. So this is how you can calculate some of the example which is maybe in the assignment problem. There are not many example, but you need to prepare this kind of example for your final exam and SEM exam, as well as sometimes your conceptual knowledge in your university or some different kind of application we are dealing with. You need to understand how this designing process of different on the basis of different solid fluid reactions are taking place. So fundamentals are if you need to understand first. Okay. So another example in that, calculate drag force on the submerged sphere. The sphere is already submerged in air stream with the following property. Obviously properties are directly given, so we can consider them. So here then velocity is given as 28 meter per second, which is very high velocity. You can consider it because it's air, so air doesn't have that much more drag force, and friction is also less. Drag force is the same thing, and density and all are also you can consider. For the air is only 1.248 kilogram per meter cube, and the viscosity of the fluid is 1.9 into 10 to the power minus 5 pascal into second. So you need to find the drag force, not drag coefficient. You need to consider that. Always remember, this is the drag coefficient. Okay, F by A, FD by AP, rho V square by 2. If you want to find the drag force, then you need to do like that. So 0.5 rho V square AP. You have to substitute the value on this. So first of all, we need to find the Reynolds number, as it is. Always we need to start with Reynolds number. From that you can find the value of CD. I already supercritical. Put the supercritical. Anyway, maybe in this tablet I think have some problem. Okay, then Reynolds number you will get rho ut dp by mu 7724 into 10 to the power 4, and this is definitely it is more than 10 to the power 3. That's why CD value is constant and preferentially we can consider it 0.44. And if we put the value in this equation, 0.5 CD rho V square into AP. I just forgot to put. So if you substitute all the values which you have, and then you will get the value of FD, which is nothing but the drag force is 0.298 Newton. This is how you can calculate the drag force. Then drag coefficient is the same thing, and then according to it you will go for the next calculation if it is required. Now there is another example. In that settling of an air droplet in air at 338 Kelvin and 175.3 kilopascal is there. Assume rigid spherical droplet of diameter 28 micrometer with the density 780 kg per meter. Calculate its terminal velocity of density and viscosity of air are 1.145 and 1.689 into power minus 5 pascal into second. This is the air is the medium. This is temperature, which I don't think it is required in our calculation. But yeah, if you want to use some charts, then it is important. This is temperature and pressure. This is the diameter of our spherical droplet, and this is the density. All droplet we need to consider as a solid. So solution, first one has to find out the flow regime, obviously in which particular droplet is settling, and then that can be known from the K value. We need to find the first K value. From K value you can consider it's either Stokes regime, or it is a regime, or it's Newton's regime, or it's in between. So if we go for the dp value of the finding the equation of the K, which is equal to dp rho gp rho g delta rho by mu square 4 raised to 1 by 3, or the cube root. So if we go for the value of substitution, the value of dp is 2.8 micrometer 10 to power minus 5, 28 into 1 minus 6. 9.81 g rho is 1.145, difference of the densities, and there is a viscosity square, and 4 raised to 1 by 3. I forgot to consider it, but at the end this is the true value, which is not wrong. And the K value is less than 2.6, then we can consider that it is in Stokes law regime. That's why Stokes law can applicable. For the sphere swelling in the Stokes law regime, the equation is very easy. G dp square rho delta rho by delta mu. You need to always remember this kind of formula. It is where everywhere in the fluid mechanics also, and mechanical operation also, and you have to get examination sometimes. So ut is equal to 9.81 dp square, already did, delta rho, and value is there. So value of ut is equal to 0.0197 meter per second. This is simply, you need to substitute the value and you will get the answer. Now you consider the motion in the centrifugal fluid. I didn't discuss more about the centrifugal fluid, but we just discuss about the gravitational field. If we discuss about the centrifugal field, then there may be centrifugal motions is there, centrifugal force you need to consider. Then centrifuges increase the forces on particle manifold compared to the gravitational force. Centrifugal force has the force value is more than the gravitational force. Thus particle does not settle steadily or does not settle at all in gravity can often separated using by centrifugal force. If we can't able to separate the particle on the basis of gravity or settling, then we can go for the centrifugal force. High settling force means that practical rates of settling can be obtained with much smaller particles than in gravity settlers. High centrifugal forces do not change the relative settling velocities of small particles, but these forces do overcome the disturbing effects of Brownian motion and free convection currents. So we need to consider centrifugal forces do not change the settling velocities of small particles, but for the forces they can disturbing the Brownian motion and free convection currents. Mechanics of motion of particles in a centrifugal field. So for the mechanics of motion, you can consider if an object is rotated in a container, the contents of the fluid and solid exert equal and opposite force called centrifugal force outward to the walls of the container. This force causes settling or sedimentation of particles through a layer of liquid or filtration of through a bed or filter cake held inside a perforated rotating chamber. For all, this is important. If you don't want to call too much detail, then calculation with the centrifugal field, on your equation, you need to replace the value of G with R omega square equation for considering the calculation using centrifugal field. So you don't need to remember all the other formula. You have to just replace the G with R omega square. Now we discuss about the hindered settling. So hindered means hindrance means there is some is the resistance is there. There are many in suspension many false particles there. In first we consider one solid particle, then other particles may hinder the motion of the first particle. Then how can we go for the settling? So large number of particles are present in suspension as we discussed. Then these surrounding particles are interfere with the motion of the individual particles. Then this obviously they interfere with the motion of particles. Then settling particle displace the liquid and appreciable upward velocity of the liquid is generated. Therefore velocity of the liquid is appreciably greater with respect to particle than with respect to apparatus itself. So velocity of the liquid is too much greater with respect to the particle. For hindered flow, settling velocity of particle is less than that of the free settling velocity. You have always need to consider, if we consider the hindered flow, the settling velocity particle is less than that of the free settling. Obviously, with free settling there is no hindrance, there is no resistance, then the particle density settling velocity is much higher. Through drag force is greater than the suspension. Viscosity of suspension or mixture, you can consider that value of the viscosity is actual viscosity divided by the empirical correction factor. Okay, so like that you can consider the viscosity value for hindered settling, and here empirical correction factor depends on the volume fraction of the slurry mixture when you occupy by the liquid. That is a function of the volume fraction of liquid in the slurry. Now the value of empirical correction factor is given by 1 upon 10 to power 1.82 and multiply by 1 minus epsilon. So epsilon is obviously porosity, and the suspension settling velocity in Stokes regime is given by this same equation. There is some little bit change is there. You can consider the change is like psi p into epsilon. So us is equal to g dp squared delta rho epsilon upon 18 mu, and here g dp squared delta rho by 18 mu, and the value of this we just consider the value of psi p. You put the value of viscosity over here, and at the end you will get the relation that us is equal to the velocity in the hinder settling is equal to terminal velocity is simple and multiply in the product of epsilon square psi p. Like this, Reynolds number in the suspension based on the velocity relative to the fluid. So Reynolds number is Reynolds number ps is equal to Reynolds number particle into rho m by rho epsilon square psi p square. So this is how you can go for the calculation of Reynolds number in the Hindra settling particle suspension, when you don't need to consider Hindra settling or something, but there is suspension is there. So how can we go for the Reynolds number calculation and the velocity calculation? So, and there is one another correlation. If we consider that ut is equal to in the form of us and epsilon raised to n, then what is the value of n? It depends on the which is your regime you are talking about. So like that, if your Reynolds number is 0.1, if you talk about the Stokes regime, then your value of n is the value of n is 4.6, and then we are considering Newton's regime, then your value of n is equal to 2.5 only. This is how you consider the Hindra settling, and this is the difference between the equation of the simple free settling velocity and suspension settling velocity. Simple Reynolds number and suspension based Reynolds number. So I just actually there are no many questions. In fact, in this kind of example kind of questions of this Hindra settling, but you need to prepare. So that's why I just attached the same questions which already solved from the professor, and we just little bit we go for that how we can consider the solution of this suspension or Hindra settling velocity phenomena. So calculate the Hindra settling velocity of the glass spherical particles having a diameter of dp. This is the diameter value of the glass spherical particle in the water at the temperature of 20 degrees centigrade. The slurry contains a 68% solid. Here it is mentioned that it contains the 68% solid. The solid density is 2467 kg per meter cube. The density and viscosity of water at 20 degrees centigrade are 998 kg per meter cube, and this is the viscosity. This is the density and this is viscosity. We just need to use the equation which is just different. So here density of particle is 2461 kg per meter cube. Density of water is 998 mu water, and weight fraction is 60%. So here we need to find the fraction epsilon. So here 60% is the particle, the slurry, then the 40 is the water. 40 divided by density of the water 998, 60 divided by density total fraction, right? 60 divided by 2467. So at the end you will get the fraction epsilon is equal to 0.62 622. Now you can just consider the value of the rho m, density of mixture, epsilon rho plus 1 minus epsilon rho. Substitute the value, and at the end you will get the density of mixture is 1553 kg per meter cube, and the important parameter is psi p. The value of psi p is equal to 1 upon 10 to power 1.82 1 minus epsilon, and you have to substitute the value of epsilon, which is nothing but 0.622, and at the end you will get the value of 0.205, which is the value of psi p. Now we already have the equation of the settling velocity in suspension. So us is equal to g dp square delta rho by 18 mu into, this is the common equation, and into epsilon square of into psi p. Now you have to just substitute the values 9.81 into 1.554 whole square into 10 to power minus 8, and density difference is we consider 2461 is the density of particle and 998 is the density of the water. Particle is cumulative density, you need to consider solid density, and divided by 18 into mu viscosity. So as you can consider the value, if you substitute all the value into the equation, and at the end you will get the velocity in the suspension is around 1.5 into 10 to power minus 3 meter per second. At the end, if you want to find the Reynolds number for the same, when we consider the Hindra settling velocity or the suspension, then you can consider the Reynolds number value with small characterizing factor, which is mu by psi p into epsilon, and if you substitute all the value, and then you will get the value of Reynolds number is 0.121. Now here again I quote the references, which is much more similar than like professors, and you have to follow. The most of the discussion is from this McCabe Smith unit operation of chemical engineering. Other than that, you can follow unit operation of particulate solids and question and research and chemical engineering second volume. And at the end, I just want to thank you all with the quotation from Dr. Vikram Sarabhai. He is founder of Indian Space Research Organization and many more things. I just want to quote the things that he mentioned, that he who can listen to the music in the midst of noise can achieve the great things. And you can consider my email ID for any queries. And with this, I just want to okay, sure, okay. So I just want to stop sharing my screen, and at the end, thank you everyone for listening to this lecture, either on YouTube or in the meeting.